Hello, I'm Adrian Bowles of Gecko Technology. Today's video update is to bring you up to speed on the developments interfacing the Sperry Drilling IXO sub with the Gecko megapipe system. By way of a refresher of the concept behind the megapipe system, we'll quickly revisit the concept model of the megapipe node shown here. It has all the basic building blocks of any megapipe or megadrill system. It has an inbuilt battery pack, an RF transceiver PCB with onboard sensor interfacing, and a compact antenna designed to efficiently launch electromagnetic energy into the oil-based mud contained between the casing structure and the drill pipe. This megapipe node system is compatible with either the clamp-on node shown here or alternatively an inline drilling sub. In previous updates of the megadrill concept, we've demonstrated the nodal system transmitting data in our 30-meter drill pipe casing OBM test tank. But today's demonstration is a little bit different. Today's demonstration has three components. Firstly, the IXO sub, kindly provided by our project partners, Sperry Drilling. Many thanks, guys. The second component of the system is a scaled demonstrator of a multi-nodal hop. So the IXO sub communicates with the first element of the megadrill system via a simple digital serial link. This first part of the megadrill system, our bottom hole interface node, contains onboard sensing capability just like all of the other nodes in the system. So in this demonstration, the interface node contains a commercial pressure and temperature gauge, onboard accelerometer and inclinometer. The bottom hole interface node collects data whenever it is transmitted from the IXO sub. It appends its onboard sensor data and then it modulates that data on top of an RF carrier which is transmitted to the next node in the string. In a real-world deployment, that RF signal would be sent to the antenna that we previously mentioned, which would propagate the energy through the oil-based drilling mud. However, for the sake of a scaled demonstration today, we have replaced that pipe string and oil-based mud with a coaxial cable, as the propagation of electromagnetic energy through a coaxial cable with its inner conductor and outer conductor is not dissimilar to the way energy is sent through our drill pipe casing coaxial structure. The only additional thing we've had to add is a significant RF attenuator in line with all the coaxial cables, because the attenuation of electromagnetic energy through drilling mud is significant, and so to accurately represent a multi-nodal hop system we need a significant RF attenuation in line. In this case we're using a 40 dB attenuation, so the signal is reduced to a power of 1/10,000th of that initially transmitted by the time it reaches the next node in the string. So the packaged data sent via radio frequency energy is sent to the next node in the string. It then boosts that signal, it appends any sensor data of its own, and then it passes data to the next node in the string. And that ripple of signal, of data, works its way right up the string, which is itself connected by digital serial link to the PC running the bespoke software. So now we move to the final part of the system, the topside display software, which is instigating control of the network and display of any onboard sensor data. As you've seen, there's a network of 20 nodes in today's demonstration, and the first thing we do when we're running in hold or when a network is deployed is we instruct each unit to form a part of this chain or this mesh network. So we instigate the mesh formation, and immediately we are told by the ripple of communication that's worked its way up the network, where each node has informed the next node in the chain of the nodes that it could communicate with, that were within its communication range. And that ripple of information works its way up to the topside device, and we get a table that tells us, for example, that node 1 can communicate with nodes 2, 3 and 4, but it can't communicate any further. It can't speak to 5 because of that high attenuation we've inserted into the string. And to speak to number 5, it needs to talk to number 2, and number 2 can talk to number 5. And that works its way right down the network to our bottom hole device, which, as I explained, is connected by serial link to the IXO sub, and then data then passes its way back up the network, back to 0, which is our topside controller. So when we have a nice stable mesh running like that, if we like, we can simulate node failure. So I'll remove the batteries from the connection from 2 units. I'm just doing that now. 1 node and 2 nodes. And what we should see is the mesh notices that units 5 and 14 have failed for whatever reason. Maybe perhaps their batteries have run out, and so nodes 5 and 14 are now not in the mesh, and of course that means that node 2 can no longer talk to node 5, but the mesh is still stable. The bottom hole device is still in the network chain, it still knows it's part of the network, and so this is how we build in resilience within our network. So we have a stable network. Now we can go and look at some of the sensing data that's on board. So we can look at onboard vibration or inclination data. Clearly there's no data from 5 and 14 because I've taken those nodes out of the network. But no, any of these nodes the data from these nodes can be trended with time and selected for more detail. We can also have a look at any of the onboard sensors that are enabled for pressure and temperature logging, and here we have the pressure and temperature in the lab today. But most importantly, we're now going to have a look at the data that's being passed up real time from the IXO sub that we're calling here the bottom hole assembly data. So the last software screen we'll show today is that of the bottom hole assembly data. In the top left box we're getting the data direct from the IXO sub via a serial cable, 17 byte strings, one string every 4 seconds, equating to about 34 bits per second data rate. And then from the same source but via the Megadrill 20 hop link is the next hex encoded string below the IXO data, and then we've translated that hex data just into numeric data in these 2 graphs, and the overlay of the red and the white lines and the fact that this LED is lit up for the data match show that we're not getting corruption in these packets at this time. However, if I was to disconnect the connector that's taking the Megadrill link data and passing it to the computer, I'm disconnecting that now, we'll see that the Megadrill data is now blank and is now no longer being received. Obviously we're no longer getting a data match, and so the system is aware that, well, either there's a corrupt packet or there's a missing packet. If I now to plug that digital connector back in, then our Megadrill link data reappears, and we've got a data match without corruption. Alright, thank you for your time.